In this video, we're going to take a look at percent composition of a compound and how we can use percent composition of a compound to get to chemical formulas. So percent composition of a compound is exactly like it sounds. What is the percent breakdown of each element that makes up that compound? So this is simple to do when you have the entire mass of a compound and you also have the mass of each element that makes it up. It's a simple proportion of part over whole. To get the percent mass of any element within it, take the mass of the element that's in that compound, divide by the mass of the entire compound, times 100%. However, oftentimes we don't have that kind of data. We don't know how much mass there is of each element in the entire compound, so we have to look at its chemical formula. And by looking at the chemical formula, we can find the molar mass, and that gives us a breakdown of how much mass there is from each element per mole, and then the law of definite proportions tells us that that ratio is always the same no matter how much and how little you have, because all the way down on the smallest particle level, whether it be a molecule like water, H2O, or a formula unit like sodium chloride, NaCl, that ratio remains constant no matter how much or how little you have. So we can take the mass of the element within 1 mole of that compound divided by the mass of the entire mole of one compound times 100%, again putting part over whole, and you can get the percent by mass that way also. And since, again, that is a constant ratio, we can actually use that as a conversion factor. If I know that it's 45% by mass of oxygen and I had 150 grams of that oxygen, then I know that there are 67.5 grams of oxygen in that 150 grams of that compound. So let's take a look at the more simpler one first. If I have some sort of compound made up of magnesium and oxygen, and if I heat it and decompose it and break it down into its components, I find that there's 5.4 grams of oxygen in this compound that was originally 13.6 grams in total. Now we know that magnesium and oxygen gets together in a 1-to-1 ratio because magnesium is in group 2, oxygen is in group 6, so therefore it is always that 1-to-1 ratio, Mg to O. But again, just looking at it experimentally and what the mass is of each compound within it versus the entire mass of the sample we had, then we can still get that information just like if we had the molar mass. So in this case, we'll analyze known and unknown. And I know I have 13.6 grams of that magnesium-oxygen compound. I also know within it there's 5.4 grams of oxygen. And I'm trying to figure out what is the percent composition. So again, I need a part over whole. This is really simply done for the oxygen. Since I already have the part and I have the whole for the compound, I can just put that 5.4 grams of oxygen over the 13.6 grams of the entire magnesium-oxygen compound times 100%, and I find that there's 39.7% of oxygen within this particular compound of magnesium and oxygen. Now to get the percent by mass of magnesium, we could take the 13.6 grams of the compound we had, subtract the 5.4 grams of oxygen that are in there, leaving us with 8.2 grams of magnesium remaining. Or more simply, we can just take the fact that it's only made up of two things, and the percent magnesium is therefore going to be that 100% that would be the whole, minus the 39.7% that is oxygen, leaving us with 60.3% that must be magnesium. Since again, there's only two components in it, they have to add up to 100 because 100% is a whole. However, oftentimes we don't have that kind of data. We can look though at the formula, the C3H8, the molecular formula for propane, and we can use that to now help us get to our percent composition. Because I know that ratio of 3 carbons to 8 hydrogens is always going to be constant. It's a fixed ratio no matter how much or how little propane I have. So I can analyze this problem, my known, my unknown. And again, I know I have propane, that's why I have to start off, and I want to figure out what is the percent composition. So the only thing I can get with the information I have is the molar mass. I know propane is made up of 3 carbons and 8 hydrogens. Carbon with the mass of 12, 3 times 12, 36. Hydrogen with the mass of 8, 8 times 1, 8. Add them together, there are 44 grams in a mole of propane. And now I can use that molar mass to get my percent composition. I have the parts that go into the entire mole, 36 grams of carbon for that 44 grams in the entire mole, and 8 grams of oxygen for that entire mole. So I can use that now to solve out the percent breakdown of each. So carbon is going to be, again, 36 grams of carbon for every 44 grams of propane. Times 100%, we find that there's 81.8% carbon within propane. And now to get hydrogen, again, we can just take the entire 100%, subtract that 81.8% that is carbon, because it's only made up of, again, those two things, and they have to add up to a whole. And 100 minus 81.8 gives us 18.1% that is hydrogen. So next we're going to look at how we can use that percent composition to work backwards and find out a molecular formula. But the first thing you can find out about is its empirical formula. The empirical formula is the lowest whole number ratio of atoms within a compound. So in like glucose, that's C6H12O6, then we find that it has a ratio of 1 carbon to 2 hydrogens to 1 oxygen, even though it's 6 to 12 to 6. And that is because, again, the ratio is going to be a fixed constant between those two things. So C2H2 and C3H3 and C4H4 and C5H5 all have the same empirical formula of CH. They also therefore all have the same percent breakdown by composition of mass, since it's a 1-to-1 ratio of carbons to hydrogens. But we can again use our percent composition and work backwards to at least get to this empirical formula, and by doing that, we'll make it easy on ourselves. So if I have percentages, again it's by mass, well, the easiest thing to get a percent of is 100. So if we assume we have 100 grams of whatever compound we're looking at, therefore, if I had 32% by mass of oxygen, that I could just say I have 32 grams of oxygen. I could pick any mass I wanted because the percents are going to stay relative to each other. But again, it's much more easy to take it out of 100 because then you're just taking your percentages and making them into grams. But now, percents and masses of different elements don't really help us out too much because they don't have the same mass, they're not in the same playing field. So we're going to take those percents and those masses, we're going to actually put them into moles, because now moles gives us a particle-to-particle breakdown of how many atoms there are of each element within that compound. And then we're going to divide by whichever one we have the lowest amount of to make it a better ratio for us, to give us some number to 1, or some number and another number to 1, because it's a lot easier to work with that 1 and then the other proportions. And then lastly from that, we just got to take that ratio and figure out how to make them into whole numbers, what we can multiply each of those by to give us a better ratio, because you can't have partial amounts of atoms. So there's a lot of little steps that are going to go along with this, but each step in itself isn't a whole lot of work. So here we're going to see a compound that's made up of nitrogen and oxygen. And again, being a molecular compound, we really can't predict what its formula is going to be because there's so many different ways that nitrogen and oxygen get together. But in this particular compound, it's made up of 25.9% nitrogen and 74.1% oxygen by mass. What is the empirical formula? So again, percents aren't very useful to us. Actually, nor will it be grams, so it's going to involve a few steps of work. But first, let's analyze, figure out what we know and what we don't know, and figure out how we can move forward. So we know again that it's 25.9% nitrogen and that's 74.1% oxygen, and we're trying to get to its empirical formula. Those percents, we can't do much with those percents, so again, we're going to make it easy on ourselves. We're going to pretend we have 100 grams, whatever this compound is, so therefore I have 25.9 grams of nitrogen and 74.1 grams of oxygen. So now I have masses, and again, we can know what we can do with masses. We can change those into something much more useful to us. But relating a mass of nitrogen to a mass of oxygen isn't all that great because nitrogen and oxygen have different masses. So it doesn't really give a good ratio as far as that formula, an atom to atom, a particle to particle ratio that we're going to be trying to get to. So therefore we need the molar mass of each of those to now get us to something much more useful. So I know that 1 mole of nitrogen has a molar mass of 14 from its atomic mass on the periodic table, and that oxygen also has a molar mass now of 16 from its atomic mass on the periodic table. So we'll start with nitrogen. Let's take those grams of nitrogen, change them into moles. So take our given, put it over 1, 25.9 grams of nitrogen over 1, then multiply it by the conversion factor that's going to allow us to get rid of grams and get to moles. So putting those 14 grams of nitrogen on the bottom now will reduce out those grams of nitrogen, leaving me with moles. And I find there to be 1.85 moles of nitrogen for that 25.9 grams of nitrogen which I started with. Now we'll do the same thing with the oxygen. So oxygen, 74.1 grams of oxygen. Again, I need the molar mass on the bottom, so that way I can reduce out those units, those grams of oxygen, getting me to moles of oxygen. And I find there to be 4.63 moles of oxygen. However, 1.85 to 4.63 isn't a very good ratio, and yeah, we can compare atoms to atoms the same way we can compare moles to moles, because at least now we're on the same level, because there'd be the same conversion from moles to atoms. We'd be dividing by 1 mole and then multiplying it by 6.02 times 10 to the 23rd atoms, so they are on the same ratio. At least now we can compare those moles to moles. But let's get a better comparison. So we're going to divide by 1.85 because that is the lowest amount we have of each, giving us now a better ratio because anything divided by itself is 1. So I know I have 1 mole of nitrogen for every 2.5 moles of oxygen. But I can't use that to get my formula because NO2.5 isn't real. You can't have 2.5 atoms of oxygen. So I got to figure out what can I do to those ratios now to make them whole numbers. And since I have a decimal of 0.5, if I multiply it by 2, right, that makes the halves go away. So I can multiply both by 2, not changing the overall ratio. So 1 times 2, I have 2 moles of nitrogen, 2.5 times 2 for every 5 moles of oxygen. So I have 2 moles to 5 moles, or 2 atoms to 5 atoms. So I know that the formula, the empirical formula, the lowest whole number ratio for this compound is N2O5. And again, it's not necessarily what the actual formula for this compound is. It could be any multiple thereof. It could be N4O10 or N6O15. But from the percent breakdown, this is the best I can do, is get that lowest whole number ratio. In order to actually be able to determine what the real formula of this compound would be, I would need its molar mass. So if I want to get to molecular formula from the empirical formula, again, I know it's some sort of ratio of those atoms in some small whole number ratio to then get to the actual formula. So if I take the molar mass of the empirical formula, compare it to the molar mass of the actual formula, I can get what that number is. So just divide the molar mass of your actual compound by the molar mass of your empirical formula, and that'll give you that ratio of what you need to multiply every atom by within that compound. So let's take a look at how we can figure that out. Again, here we have a problem that's 1 carbon to 4 hydrogens to 1 nitrogen. That's our lowest whole number ratio we're going to be looking at for this particular compound here. But we know the real compound has a molar mass of 60. How can we relate those two things to each other? How can I take 1 carbon, 4 hydrogens, 1 nitrogen, and get to its actual formula with that molar mass of 60 grams per mole? So let's analyze this problem and figure out what kind of information we have. Well, again, reading as we go along, what is the formula of that compound? What is the molecular formula for this particular compound of carbon and hydrogen and nitrogen? I know this particular compound has that empirical formula of CH4N, 1 carbon to 4 hydrogens to 1 nitrogen. I also know that the real formula has a molar mass of 60. So I need to figure out what ratio is there between my empirical formula and my actual formula. So to find the molar mass of our empirical formula, again, we take the number of atoms of each times the atomic mass of each element within it. So 1 carbon times 12, and 4 hydrogens times 1, and then 1 nitrogen times 14. We find our empirical formula has a molar mass of 30, but our actual formula has a molar mass of 60. So we can just take, again, a simple ratio of that molecular formula to the empirical formula and figure out what is the ratio between them. So that's 60 grams per mole for our actual formula divided by the 30 grams per mole for our empirical formula. We see that the ratio is 2. So now, in order to get from 30 grams per mole to 60 grams per mole, I can just double every atom of every element within that compound, and I find my real formula is C2H8N2. Again, if I were to find the molar mass of that, 2 times 12 plus 8 times 1 plus 2 times 14, that would now give me a molar mass of 60. But if I just find the ratio of them, and then whatever that factor is, do that to each of the subscripts for each atom within the empirical formula, it will give me my molecular formula, like we see here with C2H8N2.